So I want you to jump right out of the gate with a practice question. Go ahead and provide a structure for C3H8O. And that would be your opportunity to hit pause so you can spend some time to kind of draw that out. I'm going to assume that you have that drawn. So if we were to go through and take a look at that as a little bit of practice, the core on this is probably going to be looking for that C3. So we could go through and draw out each of our atoms in a line. The hydrogens being only able to bond once are more than likely going to be jumping onto those hydrogens, or sorry, onto those carbons. And if we built this out, we might just go and say, does that cover it? So we got 1, 2, 3, 4, 5, 6, 7, 8. So cool. And I would bet that most of you got that answer. And then I would also bet that most of you did not provide this as an answer. Right? And well, in theory, also with the lone pair electrons on that oxygen, because we shouldn't be implying those. And so therein lies the problem with this, is that when we're looking at our formulas could represent a whole bunch of different compounds. So we have to be a little bit more careful when looking at formulas to acknowledge that they aren't perfect. And for the most part, formulas shouldn't be what we look at. We're going to want to look for structures, because structures are going to give us more of that information about that connectivity. Because if we were to go through and look at this structure, it's relatively unreactive. Where if we switched back to the original one that I'd drawn out, this one is much more reactive because we now have that oxygen-hydrogen bond. Okay, so we get big reactivity differences depending on how we connect our atoms together, so be aware of that. But for the most part, what we're concerned about isn't the raw Lewis structure center atom, but more larger structures. And that's why we don't stress as much about the center atom aspect. We're more concerned about what those connectivities are. Okay? Excuse me. After that, the next thing that comes into play is where those atoms are relative in space, because Lewis theory, while it does a pretty decent job describing connectivity between those atoms, it doesn't describe where those atoms are in three-dimensional space with respect to each other. And that's really where we end up with the valence shell electron pair repulsion theory. That starts using Lewis as kind of the base to explain where the electrons are located, and then tries to describe, now that we know how many electrons they're supposed to be, where do they go in three-dimensional space? And that's kind of an obvious thing to see as problematic when we look at, say, just CH4, because if we drew that out, we might make that look like all the hydrogens are in the same plane. So again, CH4 as a Lewis structure, it looks like the bond angle between them would all be 90 degrees. And most people go, well, they're all 90 degrees, they're all equal. And what typically happens is that we forget that the bond angle between those two hydrogens is not 90 degrees. As drawn, it's 180, which means the drawing is not accurate, because CH4, they're all equivalent. That's why we need Vesper, and that's ultimately why we need hybridization theory as well. Okay? So the big conclusion that comes out of Vesper is that our bonds or electron orbitals will move as far away from each other as possible to generate the different shapes. And that's how we get our electron geometries. The biggest thing that we're looking at within those is that we don't differentiate between bonding and non-bonding. We really just say there's a group of electrons. For that matter, we don't differentiate between single bonds and double bonds, just a group of electrons. And we really have three primary categories: linear, trigonal, planar, and tetrahedral. If you remember from 151, there were a lot more categories. We don't care about those categories because simplified periodic table, we don't have to deal with them. So we're really just dealing with these three. But as you might also remember from 151, if we were to look at, say, methane versus ammonia, well, methane and ammonia both have 4 groups of electrons, but ammonia is different Because ammonia has a non-bonding pair of electrons as opposed to a fourth bond. Well, a non-bonding pair of electrons is distinctly different from a bond. The bond is the electrons being shared between two spaces. So if I were to, here we can use my pen, okay? If atom A, atom B, and the pen is electrons, well, those electrons are now being shared across that space. If the electrons are a non-bonding pair, they're now only associated with one atom. The electrons are much, much closer to that one atom, and that changes the shape. Right? The shapes that we're seeing with those electron geometries assumes that they're all occupying the same relative space. That's just not the case when you move to a non-bonding pair. And that's why you end up with those slight variations of those shapes, where we encounter trigonal pyramidal and bent. Being aware of what these shapes are, where they are in 3 dimensions, becomes a really important thing to be able to do and manipulate in chemistry, as I'm now frantically looking around for a model kit that I don't have built. So one of the things I'm going to recommend that you do when going through this particular unit is have some of these shapes pre-built for you so that you can see them. Build a tetrahedral methane carbon so that you have that and you're familiar with where those things are in 3 dimensions. If you don't have a model kit, you should buy one. That's why it's one of the required items. But there are kind of cheats that you can get through. For instance, you can use your hand, okay? And it gets a little bit tricky to use your hand, but we can pull this off. And with that, I'm going to try and see if I can't get this picture a little bit bigger. Cool. And if we take a look at my hand, I got 1, 2, 3 groups of electrons, okay, across those 3 fingers. That 4th group of electrons is going to be my wrist. So what I'm going to do is kind of turn it, and you now have my wrist as one group. There's another group. There's something coming at you. There's something going away, that thumb in the background. And what I'm trying to represent is that drawing sliding directly to the, that would be right, I think. There's no inverse here. I think that's to the right of that tetrahedral. Okay, and we look at it, we have in the plane shown as a solid line, and then my wrist, solid line, that's 109 degrees if you assume that I've got that correctly drawn out. We've got that thing coming at you, that's our wedge, okay? And as I point to the screen, that's the wedge on that tetrahedral drawing. And then the dash would be my thumb going away from you. And that's representing that space. And if you kind of play around with these kits, what you should be trying to do is manipulate them in different directions to see how you could draw them. And now what we'll do is drop back to some of the kind of drawing mistakes that we could potentially do, okay? And kind of cheats. So the first, it's not really a cheat, but I'm going to call it a cheat. The first cheat, that thing, there we go, that I'm going to go ahead and draw is that when we're drawing our tetrahedral structure, it's 2 V's. Okay, so 1 V, second V. Except one of those V's needs to be wedged and the other part dashed. That's now a valid tetrahedron, again, assuming those points are connected. You will occasionally see people draw something along these lines. Wedged and dashed. Okay, and you might say, well, that still has the 2 solid lines, a wedge and a dash. Shouldn't that count? And no, okay, it can't physically exist. Feel free to grab your model kit and remember what those things represent. A solid line means it's in the plane of the paper. Okay. The wedge is coming out and the dash is going behind the plane of our paper. There is no way you can orient that tetrahedral molecule for that representation to exist. And there becomes the problem. The students will draw this and then attempt to answer a question based on this drawing. Well, the drawing is flawed, which means the answer that you get from that is going to be flawed. The sneaky, unfortunate thing behind a lot of these is that your answer is really either kind of true or false. There's really only 2 options. So you'll draw something horribly wrong, then somehow luck into getting the answer correct, and now assume your drawing is correct. Okay? You have to be very, very careful with that. Your drawing can be horribly wrong. You can use that and make a second mistake and get the answer right. So 2 wrongs end up getting you a right answer. You then make the assumption that your understanding all the way through was correct. And in fact, it was just so horribly wrong that you were right. Okay, so you need to be very careful with how you draw things to make sure that you're drawing them accurate to the 3-dimensional model. Really, the only way to do that is to have the 3-dimensional model in front of you. If you don't have that 3-dimensional model in front of you, you're relying on you mimicking exactly what's written in the textbook. Any variation off of that, i.e. an exam question, you're now guessing. Okay? And for those people saying, well, I guess really luckily, that's cool. You can be right 75% of the time. That's still not a very good score. Okay? So what I want you to do is focus on looking at those models and trying to represent the different orientations of those drawings. As we continue to move through this unit, we're going to see more and more orientations that you need to be able to understand and represent through the model. If you don't have that model, it's going to become problematic. Okay? So please spend some time to play with those models. Try and get used to those drawings. If we were to go through and say, I actually wanted these to be the solid, well then again, the V, wedge, dash. Okay, again, note 1 V and a second V. Those V's don't have to be on the same axis, they're just kind of aimed at each other, but never cross them. Okay, you can't get a V like this and like this, that doesn't count. Okay, that is a bad drawing. Okay, so make sure you draw things correctly. Try and get as accurate to the 3-dimensional bond angles as possible, and you should be okay. Okay? After that, this is our big shape summary. You need to be able to identify these shapes and have a rough idea of those bond angles. You don't have to have the bond angles nailed perfectly because it isn't that big of a deal. But knowing something about what those shapes are and where that places those things in 3 dimensions becomes important. We will encounter, might be the next video, I honestly can't remember, but I think it's the next video, that addresses hybridization theory. So those shapes will tie to hybridization, and that becomes important because as those S and P's represent, those were orbitals. That's where the electrons are located. And as we talked about already, with Lewis structure, it's where electrons are. So you have to be familiar with these kind of spaces. Hopefully, this just takes a quick review and you're locked on and you're golden. This isn't like a, oh my God, cram in and get it all nailed. If you really gotta, zero in on something, okay, you don't need the vast majority of this table. You're gonna spend probably a significant portion in here. Actually, I don't want to erase that line. And we'll see a significant portion here. And up here. Okay, so if we go through and try to erase all the other stuff. Those would be the critical ones to really kind of nail down because those are going to describe where those things are in space, and that's going to be helpful. Right? So try and keep your focus on making sure that when you draw a Lewis structure, you can label the shape for each atom, and that becomes an interesting question. For each atom, we aren't looking at for the molecule, we're looking for whatever our center atom is. That center atom can be massively different depending on what we're looking at. Remember that CH3 thing that we started this whole lecture with? Okay, come on, pen. If we were to go through and look at that in really small, what did I say, 3? Already I kind of goofed from where I wanted to go, but hey, we got it. And if we looked at this structure, we don't have a center atom to identify that shape, but we could say that that green carbon is tetrahedral. That green carbon is also tetrahedral. Oops, that green carbon is tetrahedral. And that oxygen would be tetrahedral electron geometry, but more important for us would be the molecular shape that is bent. So this drawing, while it is an accurate Lewis drawing, doesn't accurately represent the 3-dimensional shape very well, and I might be better served by spinning it a little bit and showing this as the shape. because that better represents how that molecule interacts. And what it helps to show is that I get this kind of hangout of electrons on one side of the molecule. Those electrons are now more accessible and potentially more reactive. So that shape helps me to come to those conclusions. Lewis structure doesn't show that shape. You have to kind of interpret it using Vesper to get it into that proper formation. Okay? So, Vesper Applied. This is kind of fun because it's nomenclature. And you're like, but we haven't talked about nomenclature yet. This is where it becomes kind of weird. The very next video link, you're going to start seeing some references to nomenclature. You should be going through and doing nomenclature. It is my least favorite section. You need to know some parts of it. Okay, so what we'd be doing is looking at how those rules break down and what they mean. So I'm going to talk through some of those applications here because they're kind of relevant and kind of not, so I'm not super stressed about it. But start looking at nomenclature. It's literally just a memorize thing. So memorize. If you want to memorize, that's nomenclature. Okay, and I'll rant, I'm sure, about it a whole lot more this semester. So let's go through and take a look at that first one. We've got really two pieces to this name, meth, believe it or not, and ane. That meth is telling us the number of carbons. That ane is giving us some information about hybridization, which at this point we don't really pick up too much on because we haven't talked about hybridization yet, okay? But that's where it's leading. And ultimately what this means is that I have one carbon, and that one carbon, there's only one carbon, it can only have one hybridization. That's not officially true. And it needs to have 4 hydrogens. So there we go. Methane. If we looked at this in a Vesper type situation, wedge, dash, and as long as we show that those 2 V's, okay, that we're aligning those properly, we're good. And we have methane. The bond angle there would end up being 109.5, okay, in each of those cases. If we break it down to the next one, we'll see again the same process, but and ane, but we also have this cyclo out in front. Well, that cyclo, core root, bicycles, motorcycles, we're talking about wheels, okay, so we're looking at cyclic. We're looking at putting 4 carbons all connected in a ring, okay. That ane means all single bonds, and we could throw on our hydrogens to satisfy our octets. Okay, this becomes an interesting one to deal with as far as Vesper with wedges and dashes. Okay, because if we go through and do this one, what we're going to find if you actually build out the molecule, you might be like, well, that was obvious. But what we're going to find is that all of the hydrogens will either be wedged or dashed. They're all going to come out on the same side, up or down from the individual structure. Okay? And that ends up being our cyclobutane. The bond angle here, well, since they were all 4 groups of electrons, we would say tetrahedral, which would mean 109.5 degrees, but because it's a ring, it has to come in at 90 with that square shape. So our structures can force geometries. Because the geometry of that carbon wants to be 109.5, but the structure is forcing it at 90, does that give you any information? Yeah, it tells me that this ring is kind of strained, and that if you were to attempt to build this with your model kit, you're probably going to have a hard time making those connections because it's going to want to pop open. Right? And depending on what model kit you have, I don't recommend building it because it'll break your model kit. Okay? What happens as we continue to move through? Let's take a look at chloromethane. So again, we've got a slight adjustment here. Chloro, we've got that meth root showing up, and then our ane. So that meth telling us we have 1 carbon, the ane telling us we need just single bonds. The chloro, I'm going to draw upwards, and we could draw on the rest of our hydrogens, wedged hydrogen, hydrogen. The bond angle here, we might again predict to come out at this 109.5. But again, that 109.5 was dictated assuming all of those bonds were equivalent. And chlorine is most certainly different than hydrogen. How? Chlorine has a lot more electrons, making it much larger, which means that bond length gets longer. As that bond gets longer, there now opens up more space in here, which means these hydrogens can kind of float up to get a little bit more space, which means the bond angle, which will become really important on the bottom, between those hydrogens ends up becoming larger than 109.5, okay? Because one of those groups kind of floats upwards. What happens if we say switch this up to bromomethane? We're going to get a very similar structure, except now what happens? Well, bromine is even larger than chlorine, which means it's even further away, which means that bond angle becomes even larger than 109.5. Okay? And what we'll find when we move into our third unit is that that bond angle on that backside dictates how fast these individual molecules will react in particular mechanisms. Okay? So these shapes dictate that reactivity. Okay? Why? Well, these molecules react by something coming in from the back side. If that bond angle is much larger for the bromine structure, it's easier to get into the backside. The reaction occurs faster. Okay? So the shape has a direct involvement in how the reaction works. Last one becomes extra tricky. As far as nomenclature goes, it kind of throws all the nomenclature rules out. We're going to have a carbon. We know it's a carbocation because it says so, so it's positively charged, which means we don't achieve a full octet. We're only going to have 3 hydrogens around it. Okay? With those 3 hydrogens around it, now that shape is going to come in and be 120 degrees because we only have 3 groups of electrons, trigonal planar, 120 degrees. That again changes the geometry of the molecule, and it changes how that molecule can potentially react in future situations. So we have to be thinking of these shapes because those shapes dictate how we interact. Right? And for those of you saying, well, shapes don't make that big of a difference, right? All you have to do is think about someone's hand. You go like, well, what do I care? You're still like, what? Get the idea? The shape can make a really big difference in how we interact with each other. Okay? So where those things are, big, big, big deal. Right? So we need to be familiar with those 3-dimensional structures, and you need to be thinking about them and ideally using a model kit to manipulate them. Okay? So organic molecules, draw the structure hinted at with C5H12. Okay? This would be, again, good opportunity to click that pause button, draw out a structure for C5H12. Okay? For those of you that went through and drew that out, I commend you because you're actually listening and doing what you're told, which is, believe it or not, a really good thing when we're talking about education, because you need to be thinking about these things. We're leading you in to help you out. And if you probably drew it out, 3 carbons, 4, 5, hydrogen, 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 it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You'd have C5H12, and you'd be wrong because that's not actually what I was asking for. What I wanted you to draw was this one for Lewis structure. Why'd you draw the wrong one? This is what I wanted. Remember how we started? Formulas kind of suck, okay? And to that end, that's one of the reasons why we encounter something known as a structural formula or sometimes a condensed formula. And what those things are trying to do is give you some structural information that you can interpret, okay? And you might ask, well, why don't you just give me the freaking Lewis structure so I don't have to deal with all that extra interpretation? That is an awesome point, and that is something that I would like to always try and do. However, you won't always be given that. And the reason why you won't always be given that is it's hard to draw a Lewis structure, okay? Particularly in a digital system. Okay? All you have to do to figure that out is have started the homework to realize drawing these things is tedious and challenging. Technology is getting better. I have no doubt that what we will do is eventually move to the point where we will just give you a structure and you don't have to do this kind of interpretation. But the system that we're in, structural formulas are easier to provide because we type. You get rid of the computer, all you're going to see are drawings. As soon as you bring in a computer, now you got to interpret structural formulas. So let's walk through that structural formula on how we move from the formula that I gave you all the way up and how that translates into that Lewis structure. So we started out, we read left to right. Okay? One of the things that can be tricky is that there are structural formulas for functional groups that really only get read left to right. And if you put them on the far left of your structure or your formula, it wouldn't make logical sense. And so the formula gets flipped, and instead of reading the structure from left to right, we read it from right to left. Okay? And for those of you being like, well, what does that mean? Well, we'll look at it. If we look at this structural formula from left to right, it's going to result in this Lewis structure. Okay, so let's start. Left to right, the first thing I see is a C next to 3 hydrogens. There's a C, 3 hydrogens. Okay, parentheses, there's 2 of them. So I draw a second one. Okay, those are connected to a single carbon. There's that single carbon. That single carbon has a hydrogen connected to it. There's that hydrogen connected to it. Okay. The next thing that it's connected to would be another carbon. You might say, well, aren't those two close to each other? Shouldn't the hydrogen be bonded to the carbon? Hydrogen can't bridge. It's kind of this vestigial limb, if you will. I drew the wrong thing. There's a carbon. That carbon has 2 hydrogens connected to it. So we bump those off the sides. It would then be missing its octet. So the next thing in the line would be another carbon with its 3 hydrogens. Okay? And that's how that one's read, right to left. Okay? But like I said, we didn't have to read it necessarily right to left. What if I read this structure, sorry, left to right? What if I read the structure the other direction? Well, that's a carbon with 3 hydrogens, followed by a carbon with 2 hydrogens, followed by a carbon with 1 hydrogen, followed by, I need a new color, drop in blue, a carbon with 3 hydrogens, but it's also connected to another carbon with 3 hydrogens, and because those are the same, I can put parentheses and put a 2. Note, I'm getting the same information embedded, but the structural formula has now apparently changed because we've changed the direction of it. We're just reading it from a different view. And if we were to go through and look at this one and follow the same kind of patterning of reading left to right, we would probably have the structure drawn the other way. Okay, so hopefully that makes sense when I say the structure drawn the other way, which is then going to beg the next question. CHHH, right? And then we connect all these bonds, bonds, bonds. What is the difference between these 2 molecules? Well, nothing. But their formulas look different and the structures look different, right? We've got that branching thing on the right side of the molecule versus the left side. So which one is correct? Well, they're both correct. We're just changing our viewpoint on it. And this is one of the reasons why we need humans to interpret a lot of organic structures. Because a computer might look at that and say, well, those are different because they're spatially organized differently. But organic chemistry is 3-dimensional. We have to be able to recognize that those things can spin, flip, and rotate in 3 dimensions so that they would be in the identical spacing. Okay? That is challenging to go through and manipulate and see, and that's going to be one of the reasons why Chapter 5 is going to become really nasty. Okay? Because in Chapter 5, we now really start to nuance how those 3-dimensional spaces can become visually similar, but very different molecules and very different activities. Okay. If we move to the Vesper, we could go through and show that those bond angles are a little bit more appropriate. Note we're seeing all those wedges and triangles and all that fun stuff within that. That gets really messy, okay? What we might do is simplify that and back away from it, okay? Remove the C's and just specify them as points. That makes it easier to see still, okay? And then we might just remove the hydrogens altogether and draw the final form, okay? Most of organic chemistry is going to spend its time looking at this, okay? Which isn't too bad. But you have to know that all of this information is there, okay? And ultimately, really, it's all of that information is there. Why? Because each of those hydrogens has a particular reactivity associated with it, and we have to be familiar enough that when we look at the red structure to know that those hydrogens could potentially react given the proper conditions. Okay? And those implied hydrogens are very often going to be the bane of your existence in getting things wrong. Okay? And this is why you need to practice this process going all the way from the Lewis structure up there to that line angle abbreviated form at the far right, so that you understand where those pieces are and how they shift and move on you. Okay? Which gets us again to looking for those patterns. Okay? You have to be familiar with what positively charged means, what neutral means, what negatively charged means, and how many bonds should be around it. Because once you have that, now you can layer on the shape. Once you have the shape, now you can layer on even more. Okay? What do we mean by more? Well, that would be our hybridization that we'll see in the next unit. Okay? So we got to put it all together. So big simplifications again. Largely hydrogen, boron, carbon, nitrogen, oxygen, and the halogens. So kind of those families sets us up nicely. Simplified shapes and hybridizations. We haven't covered hybridizations, but shapes, largely the tetrahedral categories are big one. And then our abbreviated drawings. Make sure you have these rules handy, because you need these when you go through and manipulate and draw your structures. Okay, with that, we're done with yet another video, and I believe we'll be moving into our hybridizations and kind of where electrons exist in orbitals, which is fun, challenging, and arguably sometimes maybe not necessary.